Okay, as we saw in class, these two problems are problems that are difficult to do using the techniques that we've used so far to solve limits. First thing you should always do is do substitution here. So if I do that for this first problem and replace x with 1/2, here I get natural log of 1, which if you remember, natural log of 1 is 0. And we replace it in the bottom, I get 1/2 squared, which is 1/4, minus 2 times 1/2, which is minus 1, and 1/4 minus 1 is 3/4, plus 3/4 also comes out to be 0. So this is what we call an indeterminate form. Reminder that there is an answer, I just got to find it a different way. This is not the same as, say, 7 divided by 0, which then there is no answer. Make sure you get that straight. 7 divided by 0, no answer. 0 divided by 0, there's an answer. I got to go find it some other way. So this one involved L'Hopital, who was a mathematician back in the 17th century, is credited with this rule, and he found out that if you derive both the top and the bottom, the numerator and the denominator separately, and then find the limit of that resulting fraction, it will give you the limit. So if I derive the top here, I get 1 over 2x times 2. If I divide the bottom, I get 2x minus 2. And once again, I find the limit as x approaches 1/2. Well, if I plug that in there, 1 over x, pretend these 2's cancel, it ends up being 2 over 2 times 1/2 is 1 minus 2 is negative 1. And so the limit here turns out to be negative 2. And so this is a way to evaluate limits when substitution doesn't work. And like if we try to do factoring or synthetic division, that wouldn't work here. And if you didn't have access to a calculator, you wouldn't be able to generate a graph or a table here. So this is a way to get around that problem. Okay, so the next problem, just to show us another example, it's a limit as x approaches 0. So if I replace 0 in the numerator, sine of 0 is 0. And if I replace 0 there, I get 0 squared plus 2 times 0, which is also 0. Once again, this is an indeterminate form. 0 divided by 0 means there is an answer. I just got to go find it a different way. So I'm going to use L'Hopital, and so I'm going to derive the top and get cosine x over 2x plus 2. And then I again take the limit as x goes to 0 for both the numerator and the denominator. So the top here, cosine 0, remember, is not 0, but 1. And on the bottom here, I get 2. So that means my limit is equal to 1/2. So this is a way, again, to evaluate the limit algebraically without using a graph or a table or synthetic division. L'Hopital found out that it also works when you have a different kind of indeterminate form, which is infinity divided by infinity. So if you notice here, I'm taking the limit as x goes to infinity of a polynomial numerator and a polynomial denominator. And he realized that in both cases, if you replace x with infinity, the top is just going to get bigger and bigger and bigger, so it's going to go to infinity. And likewise, the bottom is just going to get bigger and bigger and bigger, go to infinity. So you can apply L'Hopital's rule, derive each one separately. So if I derive the top, I get 6x plus 2. If I derive the bottom, I get 10x minus 3. And again, I take the limit as x goes to infinity here. And I notice here, it's going to go to infinity again, both the top and the bottom. So L'Hopital said you can do it again. You can do it as many times as necessary until you actually get an answer. So you apply L'Hopital's again, and you realize the derivative of the top is 6. The derivative of the bottom is actually just 10. And when I take the limit as x goes to infinity of this, well, I just get the fraction 6/10, which reduces to 3/5. So my limit turns out to be 3/5. So let's take a look at a different kind of problem here. So similar example here, but now we're going to find the limit as x goes to infinity of a different equation here. So once again, you got to check the top goes to infinity. The bottom also goes to infinity. So you derive each one separately. So the top one becomes 9x squared plus 2 divided by 10x minus 3. And again, you find the limit as x goes to infinity of that. And again, because of the presence of the x's there, they're both just going to keep going bigger and bigger and bigger. So L'Hopital said, apply it again. So now I get 18x plus 0 actually, so just 18x over 10. And again, I take the limit as x goes to infinity. Well, notice here, the top still goes to infinity because of the presence of the x, but the bottom doesn't have an x in it, so it actually goes to 10. Well, if you stop and think about it, and very, very big number divided by 10, 1 divided by 10, 1,000 divided by 10, a million divided by 10, a trillion divided by 10, it's just getting bigger and bigger. So my answer here would be infinity, or we could say d and e. And so this situation, we actually get an infinite answer. Okay? So let's take a look at the third problem now. Okay? And again, we notice the top goes to infinity and the bottom goes to infinity. So again, L'Hopital said derive each one separately. So 6x plus 2 over 10x squared minus 3. And again, I take the limit as x goes to infinity. So if you notice here, they both have an x in it, so they're just going to both get infinitely bigger. So again, I apply up L'Hopital's again. So the derivative of the top now is 6, the bottom is 20x. And I take the limit as x goes to infinity of that. Well again, now, if you notice on the top, there's no variable x, so this is just going to go to the number 6. The bottom one does have an x, so it's going to go to infinity. So if I take 6 divided by a very big number, 6 divided by 10, 6 divided by 1,000, 6 divided by a million, 6 divided by a trillion, you're going to get something very, very small, and the limit here would actually be 0. So if we go back and take a look at this and say, well, what did we do here? Well, if you look here, look at the answer here is 3/5, and if you look there, hey, that was actually as part of the problem. You see how the 3/5 was the numbers in front of the two highest exponents? And in this case, the two highest exponents are the same. So the limit turns out to be the coefficients of the two highest exponents. But if you look at the second example, the answer didn't come out to be a number, it came out to infinity. But if you look at the relationship here, you'll notice that the two highest exponents aren't equal like they were in the first problem. The first one has a limit as the highest exponent of 3, and the bottom one has a highest exponent of 2. So notice the bottom one is smaller than the top. And that's a situation in which the limit came out to be infinity. In the last problem, if you notice here, the bottom exponent, highest exponent, was actually bigger than the highest exponent on the top. And that answer came out to be 0. So this shows a shortcut here, that when you're evaluating limits with polynomial functions, if you look at the two highest exponents and they're the same, then the limit is just the numbers in front of those two highest exponents. If the top exponent happens to be higher than the smaller one, the bottom one, then your answer will be infinity. And if the reverses happen, where the bottom one is actually bigger than the top one, then your answer is 0. So there's some shortcuts here that kind of allow us to get around even L'Hopital's rule in these unique situations. Okay, hope that helps, and good luck.